Welcome back to the PES live streams. This one here will be a bit of a chance for you to catch up. I'm going to go through some stuff that I did notice from the assignment, but I would like people to ask questions. If there's not many questions, I might just keep this one short. If you are watching, you can join with the Hangout link. Also, Josh isn't joining us today. Sorry, it's a little bit more difficult. All right, so if you're there and watching, you can join the Hangouts or ask a question in the YouTube chat. If there's some specific topic you'd like covered, please let me know and we can cover that. There's no set topics for this one because the next one will cover the material for that week. All right. So hopefully there's a couple of people here because I have noticed there's a lot of people still falling behind. All right, so what I might start with, that's not what I wanted to do. Let me just set this up. Sorry. If you are there, join the chat or write what you would like to do, because I don't know what you're stuck at. What I would like to go over is something that was covered many weeks ago, but I'm still seeing people make mistakes. And that is with functions. So in this program here, I've got my int main. And what I want to do is take this number and square it with my own function. So what I'm going to do is, I know that I've got my number, but I want to square it. So I'm going to create a function called int square. I know I need to return an int because our variable is an int. And to square a number, all the information I need is some variable that's also an int. So we need to now, this is our declaration or our function prototype. We also need to actually write our function. You can see here that we have int x here. Now, what a lot of people are getting confused about, and what I've noticed, is that people will write square int x or something similar. You can't do this because you can't declare a variable inside a function call. However, here, this is the function, and so we are creating the variable when we start. So one thing, oops, don't do that. So it should always be the arguments that you're passing, and you shouldn't be declaring. It is declared here. We'll go through the example. So if I want to square x, I can do this a couple of ways. I'm going to do it the long way first. So I'm going to create another variable called temp, let's say, and go x times x, and then return x. So now what I can do is call my function. So up here, I can go square num. Now what this will do is it will put a 4 here and pass it into my function such that x takes the value 4. 4 times 4 is 4 times 4 is 16, and then it will return that 16. Now, the problem with the code so far is that I haven't restored this result. So with some functions, we don't need to restore the result. So for example, printf. Printf does actually return something, but we don't usually store the result. So it's usually not something like x equals printf. Same as scanf, we don't usually restore the result. However, something like getCar, we often do. So if you've got this int here, then, and you're returning something useful, you should be storing the result somewhere. So let's create another variable, and let's call it int w equals square num. Now, the good thing about having these functions declared is now if I wanted to square, let's say w, I can do that quite easily. And I'll just add a return here, and then let's go through our program step by step.
Yeah, in some time.
Sorry. Okay, so now let me just zoom out. So this is our program now. So let's just quickly go through it and see what's happening. Oh, I need to do that. So up in main, let's say this is main, we have one variable called num, which we created. So we're on this line here. And it's an int, and it has the value 4. We then create another variable called w, and it's an int, but on the left-hand side, we call this square function and we pass the 4. Okay, so we're on this line. So when we do that, we can't see above this line now. We can only see below it. And this is our square function. So in this declaration, we create a new variable. So when we call the function, whatever is in this line, so if we have 10 parameters here, then it will create all 10. If we have 2, it will create 2. So this is x, and it's an int, and the 4 will go in here. So I can't refer to num inside this function because num is only declared up here in main. As I said, I can't see anything above that line. So because num is the first argument, it will pass the value 4. Okay? Then we come to this line and we create another variable called temp, which is an int. 4 times 4 is 16. And then we have this return. So the return returns the number 16 back up here. And where it gets stored is into W. So now we have 16 here. Everything below this line is now gone because we've left our function. Okay, so we're left with 4 and 16. We then call square again. So the 16 is passed, and it will create a new variable, whatever's here, x, and it's an int. The 6 gets stored here, it gets passed in as the first argument, and then we create our temp, int 36. And then we pass back temp. Okay? And so this gets stored in W and we get 36. And everything below here is gone. Okay? So you should know how to call and use a function. This is really, really important. Does anyone have any questions on that? This is from weeks and weeks ago, but we're still noticing a couple people have problems with it. Okay, so I'm going to find another. So this is actually a question that was in the quiz. So I'm going to have a look and find other questions, unless you want to type something. Where's the quiz questions? Sorry. Okay. Now, what I want to do is this time I'm going to change my function. And what I'm going to do is make this a pointer. And I'm going to change this to void. Okay, so if I change it up there, I need to change it here as well. Now in here, if I'm using a pointer and I want to change its value, so I can still have my int. I'm not going to do that. I'm going to do this instead. I'm going to go star x equals star x times star x. Okay, so this time I'm going to use pointers to change the value of x. So now I don't need this return because my function is now void. So I'm going to change this to num. And I'm going to move this stuff across. Alright. Now, this is a very basic example, so you should, oh my god, keep doing that. So you should be able to solve this, but just make sure that you can draw the diagrams as well. Okay, so in this one, we've changed our function, so now it's void square int star x. So passing a value is not going to work because a pointer needs a memory address. So we also need to change these. So a good check to know if you're sending the right thing to a function is if you've got your function. So let's say this is my function. Int x, int star, y, car, z. Let's say it's that. And when I call my function from somewhere, so this is a different example, I should see if I've declared int x, int y, and car z. Let's say int star y. When I call the function, if these match, so this is an int and this is an int, then I can just pass x. This is an int star, this is an int star, so I can just pass y. This is a car z, this is a car z, so I can just pass z. Okay? However, if I want to pass the address of x here, let's say, then int, and this is an int star. So to get the address of x, so the y can point to it, I have to send the address of x. Okay, so hopefully that makes sense. You can't send something of a different type to a function. Well, you can, but if they don't match, you know you need to do something. Okay? So that's a good way to check. Do they match? If they match, you just send the same variable. If they don't match, you are likely to need to dereference it or send the address. So here, because this is an int star and it points to the address of an int, and this is an int, so we need the address of the int. So we add the and symbols. So now if we go through this problem, we're up in main, we create our variable int num, and it has the value 4. Okay, we then pass the address of this variable into our square function. So in here we create, as I said, when the function's called, it creates all the variables here. So now we've got x and its type int star. So now this here has the address of this. Okay? Because we passed the address. So we're here right now. Now, when we look at these stars, we are dereferencing. So let's look at the left-hand side first. So dereference x, follow the line and grab the value, is 4. Follow the line, grab the value, it's 4. So now we've got 16 on the left-hand side. This star, because it's, on the right-hand side, sorry, because it's on the left-hand side, we change the value at where it points. So we follow the line. Now, the stars tell you how many lines to follow if you're using this diagram. So now this becomes 16. Okay, then we end the function. So now we lose this, and we don't have this pointer anymore, but we've changed the value to 16. Now, what we do is we call the function again, and once again, we pass the address. What am I doing? So we're here now. We create our variable, which is x, and it's the type int star, and we have the address of this one. So looking here, we've got x, and we need to dereference it, so follow the line. We grab a 16, 16, grab the x, there's 1 star, so we follow the line once, 16, and then we change the value at x, so we get to 56. Then the function ends, and we lose this. So you can see, using the pointers, we don't need to have a return function, and it means that we can return more than one thing. Okay, so that's 2 important things that people have had a bit of trouble with in terms of the assignment. Now, let me just go to the next thing I've listed, unless anyone has any questions. If you've got questions, join the chat or join the Hangout. I'm looking at both. That's fun, but I think there's more important things right now, especially after seeing the assignment. Okay. This one is really, really important. Okay, so one thing that I have seen people do is when they use macros, they use them incorrectly. So let's say I've got int main, and I want to do a calculation. Let's say int x equals x. No, not x. Let's say it equals number of students. And then int y equals number of students times 4. So I put this all in capitals because it's my macro. It's something that I use often. Now, what I have noticed a couple of people doing is writing this. Okay. This is wrong. Now, the reason it's wrong is because when you have macros, what it basically does is just replaces what it finds here with what it finds here. Now, it'll take the first one. So when you run your code and it compiles, basically it is changing your code into this, which is wrong. Never put the equal sign here. The same thing goes. So now it will replace them correctly. So we get 4. And our code is still legal. Another thing I have noticed people do is put a semicolon here. Now this would change your code to this. So this is wrong. We can't have int y equals 4 semicolon times 4 semicolon. Okay, so be really careful with your defines when you do that. All right, what else do we have? Okay, so the other thing that I saw in the assignment was, let's say int let's say this is, I don't know, A. Now let's say I want n plus 1 ints. Okay, so I've got my n from my user, which equals 4, and I want to use malloc to create n plus 1. So I call malloc, and I do my size of int. Yeah. And then I times it by n and plus 1. Now, this is wrong. Okay? The reason being is that we need to allocate n plus 1 ints. Now, an int is 4 bytes. N plus 1 is 5. So 5 times 4 is 20 bytes. However, here we are going 4 times 4 plus 1. So we end up with 17. So we're 3 bytes short. Okay, so this is just purely mathematics and how you bracket stuff. Make sure you bracket stuff correctly. Okay, it does make a huge difference. Okay, now what else do we have? That's boring. Okay. Now, how many people are watching? How many people are in here? Not many. Okay, so what I'm going to do next, because it was asked, cool. Okay. All right. Now, what I've been asked in the Hangout, and I've lost it again, is recursive functions. So a recursive function is one that calls itself. So maybe I'll step back before we do that. So a function can call a function. So if I have, let's say, int func1, int func2 is my function prototypes, and I have int main, and I have a function that goes, let's just say, it calls func1. And then my func1 calls func2. And let's say func2 prints a message. Okay, so this is basically a call from another function. So this function calls this function, and this function calls this function. And then this will go back up to here. This function will end, and then we go back up to here. So you can see that we call a function from another function, from another function, from another function. Okay, so what if a function calls itself? So let's change this. Oh. So you've got two options with recursive functions. You can actually have this function call function1 and it still can be recursive. But the simpler recursion is this. Now, with this, recursion is generally seen as bad practice nowadays. If you can do an iterative solution, it is better. I'll explain why shortly. It's fairly technical though, the reason why. I lost my colors. So if I do this, the problem is that it will keep calling itself forever. Okay, so we enter an infinite loop. So we have func1 calling itself, calling itself, calling itself. So this is bad. Okay. However, what I want to do is show an example of where recursion can be somewhat useful. I say somewhat because there is better solutions than using recursion. Okay, so hopefully everyone knows what a factorial is. So factorial n is basically 1 times 2 times dot 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 n. Okay, so factorial 2 equals 2, because it's 1 times 2. Factorial 3 equals 6. Factorial 4 equals 1 times 2 times 3 times 4. So we've got 12, 24, and so on. Okay, so this is actually a good example of recursion because it's a function that repeats the same operation over and over again until it reaches a certain point. So let's create main. And let's create a variable called n, and let's give it 4. I'm going to go, yeah, 4 will do. Now, we call our factorial function, which returns a number as well. Let's call it w. And we're going to pass it n. So our prototype will be int fact int n, let's say. Okay, so we've got our prototype, we've got our function, and now we're going to write our actual function. So fact int n. Remember, these two are the same. But one thing to note is that you don't actually need to write the variable name up here if you don't want to. All right. So this is a really common problem. So what we want to do, so we saw before we had 4 times 3 times 2 times 1. Now, basically, if we look at the largest number and keep going down until we get to 1, then we finish. So what we can do, we have this 4 already. So we know to stop when n. So there's 2 ways to do this. We can count the 1 or not count the 1. We're going to count the 1. What I mean by that is anything times 1 is going to be the same, but for completeness, we'll consider the 1. So while n is greater or equal to 1, what we want to do is basically return. And what I want to return from this function is the 4 times by the 321. So how I will do this is I will go n times fact n minus 1. If n is equal to 0, so n minus 1 has gone to 0, then I can just return 1. Now, the definition of 0 factorial is 1. Okay, so that's perfectly legal. So now we've got a recursive function. So let me zoom out and let's run through it. So this is a little bit more complex than our normal functions, but we'll also explain why, if you can avoid it, try to avoid it. Okay. So, where are we? We've got main. Oh my god. We have main. Okay, main's up here. And we create this variable n, which equals 4. For something like this, you'd usually ask the user, but we don't want to do that. And we have a variable w, so int, and then we call this function fact. And as I said, we pass this 4 down to our thing. So now we've got n, int, and it has a 4. So we're here at the moment. Is n greater or equal to 1? Yes. So then we go here. Now, this gets evaluated first before it returns. So we've got 4 times our function. So we now have another function call, which is going to pass n minus 1 in. So it's going to pass 4 minus 1 in. So we now have another function fact. So this one here is currently stuck here because this hasn't been resolved yet. So we now have n int is 3. That's a really bad 3. Is 3 greater or equal to 1? Yes. So it gets here, and we have 3 times fact n minus 1. So now it's stuck here because it has to call and wait till it returns something. Probably should have done 3 instead of. So now we call n int 2 because it passes 3 minus 1, n minus 1, n is 3. Same thing. So now we've got 1. And then we call the last time. So here we passed 2 minus 1, and here we're going to pass 1 minus 1. So when we get to the last one, we have n is an int, and it has 0. So is 0 greater or equal to 1? No. So it's going to return a 1. So we come back up here, and we get a 1. So now we're here in this one. So this one's done. Okay, it's returned a 1. This is now a 1 times a 1. This is why I said you could just do n is greater than 1, but for completeness, for the definition of a factorial, we included it. So this now returns 1 times 1, which is also 1. So this function's done because it's used its return statement. This function will go 2 times 1, which is 2. Then this function's done. Let's return something. Then we get, where are we? We get 3 times 2. I did that the wrong way. We get 3 times 2, which is 6. And then we get 4 times 6. Did I do that right? I think so. Sorry about that. All right, which is 24. Just give me a sec, sorry. Sorry about that. Okay, so we return 24. So now W equals 24. Okay, now the reason that we want to avoid doing this is because when we're down here, all of this information is on the stack. So if you want to look at about stacks, this is why it can be a bad practice, because if this gets longer and longer and longer, all of this information need to be stored. And all of these functions need to be stored as well. And so you can run out of memory really quickly using a recursive function. So hopefully that answers your question, but it can be dangerous to use them unless you know how to get them. And generally, you try and avoid them. Does that answer your question, Yellow? Cool. All right. Now, let me grab the assignment up and let me see what else we can cover from that, because there's quite a number of things. Or has anyone got any questions or topics or labs that they struggled with? Or something from the assignment that they struggled with? Just message it. There's no specific topic for this one. Okay, so let me grab the assignment up. That's it. Sorry. Cool. All right. So let me grab the PDF up as well. Sorry. Just grab this assignment sheet.
Matt, excuse me.
Yeah.
Yeah. So, can you please answer a quiz question? It's of week 9.
It's week 9. What?
Yeah. It's something like, which of the following successfully writes the string C is a fun to the file pointed to by FPTR? Can you please answer the question?
I can't hear you properly.
Okay, sorry. The quiz question is of week 9, and the question is
that quiz
sorry?
closed? Is that quiz
Yes,
closed?
yes. It seems, because I'm able to review.
Okay, so let me look at the quiz questions. Quiz questions week 9. Was it a command line question or a file input output?
It's file question, not command line.
Okay, and what was the question?
Yeah, just a moment. Yeah, the question is, which of the following successfully writes the string C is a fun to the file pointed to by FPTR?
Okay. If you have any questions or topics, drop them in the chat. Also. What's going on? Sorry. All right. So the question we have is, yeah, that's the only one. So this is a question we got asked, I think. Oh no, that's the wrong one. Where is it? This one. There we go. All right. Is that the correct question? Ella, is that the correct question?
Yeah, right.
Yep, cool. All right, so we have a question about writing to a file. Which of the following successfully writes the string C is fun to the file pointed to by file pointer? Okay, so we have a, this is not going to work.
So were there any other question like the same one but with different options? Because for me, the option seems something else. Like
The
maybe in
options
different order?
But they're always in a different order.
Okay.
The order's randomized.
Oh, all right.
The order's always randomized.
Yeah, okay.
All right, so we have here a question. So we have a file pointer, which is called fptr. Okay. We then have a whole heap of options. So let's have a look at the options. We have this one first, which we can rule out because we're saying f pointer equals printf C is fun. Now, printf returns an int, so this is invalid because we can't store an int inside of a file pointer. The second thing is wrong is that printf prints to the screen. We can actually change where printf prints to, so we could actually get it to print to a file, but because this is here, it's invalid. Okay, so we know it's not C. We can also look at, well, let's look at look at fputs. So the definition for fputs is int fputs car star string file star f pointer. Okay, so if we look at fputs, which is basically file put string, we can see that the character array, which is C is fun, is in the wrong spot. Okay, if we want to use fput string, C is fun needs to be at the start and f pointer needs to be second. So we can rule D out. So we know it's not C and we know it's not D. So all the rest use fprintf. So we look at our definition of fprintf. Now a good idea is to have all your definitions written up. So we have file star, f pointer, and then we have car star format. And then we have dot, 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 because this is like fprintf, it can have a bunch of format specifiers. However, in this case, we don't need the format specifiers. So the first thing first is that the file pointer needs to be the first argument. So we can definitely rule out A. So A is definitely wrong. So we're left with B and E. Now, right away, we can see C is fun without without quotes is basically just going to be, so what the compiler is going to see is C and think it's a variable, and then it'll see these spaces and you'll get an error. So the only valid answer here is going to be E. Does that make sense? Cool. All right. Is there any questions on the YouTubes? Kept losing everything. All right. Is there any other quiz questions that anyone struggled with? It was giving me a sign. Okay. Here is this one. All right. Now, other people that are in the chat, what are you struggling with at the moment? Just type, or you can speak. Is there any particular topic? So you've got to, so there's a question, is the following legal to do in C? So that's really a silly question because you have a compiler, so you can test that yourself. So the thing about C, which is really good, is that you can test everything yourself. So
Yeah,
I'm going to recommend.
but
Right.
my question was, I mean, do we ever do like this? I mean, how is the application of this? This is okay. I can understand that this has to be true because by this way we are assigning the fourth element. The fifth element of the array. The address of the fifth element of an array to the pointer, right?
Yep.
Yeah. So, but like, when do we do such things? Like when we are just giving one address to a particular pointer and we want to do something. I mean, I didn't get the application of this.
Okay, so there's thousands of applications. It depends on the domain. For strings, it's for the level you're at the moment, it's a bit hard to justify some of this stuff. But let's say, so often a good use for using pointers to point to a position. There's two reasons, and this is especially true with pointer arithmetic. Now, if I do this, I can basically start using functions that look at an array, and I can start the array from here. So I can start it from the fifth element. The other thing I can do is, let's say I don't want to touch the first 4 elements, so I can start doing pointer arithmetic. Now, the reason that pointer arithmetic is chosen over using array notation is because it's quicker. So if I do cars 4 equals 6, cars 5 equals 7 versus star pointer equals 6, and then go pointer plus plus, and then go star pointer equals 7. The reason this is quicker is because this is counting from the start of the array up and then finding the fifth element, and this one's counting from the start and then going back. This is just looking at one number. This is why pointer arithmetic is very good at performance, because when you use array notation, you're basically looking from the start and then counting up by 4. You're starting at the start and then counting up by 5. So this line here has to go cars, start at the start, go to the 4th one, then put the 6th there. Cars, go to the 5, then put the 7 in there. This will go 6, follow the line, follow where it's stored, and put the 6 in there. Plus plus. 7, put it straight in there. So often pointer arithmetic is very handy. Now, if we change this to a string, so if you're doing analysis on, let's say, strings, we may want to look at, so let's change this to a string. Car, let's call it str, and we have a car pointer. Now, we may want to look at different sentences at different points in the sentence. Now, so let's say the address of string 5, and then we have another one. We could have an array of pointers even. And this one looks at, so we can break it up and just look at the last 95, look at the last 90, look at the last, and this could be handy for some analysis. There's no way to explain every application, but yeah, there's always going to be an application. Okay. Another thing you can do with pointers and strings, if you're interested, have a look at string tokenizing, stuff like that. You'll see next week. So next week's lab, there is a file which I give you. You're not expected to understand it, but you'll see why indirection can be really helpful. And that lab will come out shortly. It's just been checked over. Well, I can get it up now if you want, but it may scare some people. So I don't know if I want to. No, I might leave it for next week because I don't want to confuse anyone. I might do it in the next one. But yeah, you're not going to know every application, but there's always going to be applications, and yeah, you can't just assume because it looks weird at your level, it's not going to be used. It's still an application. Okay. So, question: how many people struggle with the maths on the assignment? Because I can do some of that, or the malloc. Can I get some other people, please? Probably getting the total parallel impedance part. Okay, cool. All right. Okay, so the mallocing. All right. So mallocing on the assignment, the first one isn't much further than what you've done. It's just combining what you've done. Now, you really need to know how to use this because it rests on your knowledge of pointers, arrays, and everything you've done in the past. So let's look at malloc first. So what I asked for was an array of pointers that point at a bunch of rows. So when we create an array, let's say int x 4, we get an array of 4. When we use int star x equals int star malloc, and we do size of int times 4, we get something similar to this, except for we have x over here, which is a pointer. So it's basically nameless memory. So we now have a pointer that points to 4 blocks in memory. Okay. So I usually draw it like this. They don't have names, but they still do have types. Okay. Sort of. Here, x is the whole array. Now, I also usually draw a little x here to indicate the array versus the pointer to the start of the array. And this is of type int. So this is the difference between malloc and creating an array like this. When we create an array dynamically, you should be using malloc. It's better memory management, and it's preferable, and it's safer. So if you use this and the memory fails because there isn't enough memory dynamically, it won't tell you anything. It'll just crash. With malloc, you can actually recover from. So if x equals null, it means there wasn't enough memory. Okay. So, Nikhil, does that make sense so far? There's a slight delay. Yep, okay, cool. So we have that, which is fairly straightforward. So with the malloc, when we need to make a bunch of places to store all the components, we can just do int star components equals, I'm not going to put the typecast there just so it fits, size of int times n. And same with our values, equals malloc size of double times n. So them ones were quite simple. Did you have any problems with those ones? Okay, so the slightly difficult one was the one that tested your knowledge. So the other one we wanted was a pointer to a bunch of rows. So how did I write it in the assignment? Let me grab the assignment. Assignment 2, there we go. So I set it as The program creates an array of pointers to doubles. Okay, so just going on that definition, I know I need an array. So I know I need an array. I'm going to call it table or result table or something. I know its name. In the question, it says the program creates an array of pointers to doubles. So I already know that I need double star. And I know if the length is 6. Okay, so now I've got this double table, just following the description. Now, the next step says is dynamically allocate memory for each of the pointers as an array of size of number of components plus 1. So let's just see what we've got here first. So at the moment, we have 6 variables in a table, which is of type double star. And let's say this is table. Now, with this is an array, but the values here, because this is double star, these have to be addresses. Okay, all of these have to be addresses. Okay, now as we saw earlier, when we've got a pointer, so in star, we can point them to a bunch of stuff. So we've got this bunch here. Okay, so basically what we want to do is create a two-dimensional array by taking advantage of this. So what I'm trying to do is basically a bunch of stuff. A bunch of stuff. So for each of our pointers, we want it to point to a bunch of stuff. So let's see how we do that. I'm getting a bigger eraser. So basically it says, then dynamically allocate memory for each of the pointers as an array. So for each of the pointers. So I know that I have to go through 0, 1, 2, 3, 4, 5. That's each of them. Now, there's 2 ways of going about this. If I need to go through all of these, I can go the long way and go table 0 equals something, table 1 equals something. Or the more sensible way may be to do this in a for loop. So whenever you've got a bunch of numbers in a row, you can just use a for loop. So this here, let's just do table I equals. This here would be equivalent to writing, because I goes from 0 to less than 6, so it goes from 0 to 5. So it's the exact same thing as writing table 0, table 1, table 2, and so on. So we're just turning it into one line repeated often rather than writing all the lines out. Okay, so when we have to do it for each, if we've got a number of them, yeah. Some people did it this way. Most people did it this way, but either way will work. The funnier thing is this is actually more efficient, but it doesn't look good. All right, so now we've got A, which says then dynamically allocate. So I already know there's going to be a malloc. Now, table I is a pointer, so I don't need to dereference it or anything. It's a double star, so it's a pointer. So it's allowed to store what malloc returns. Remember, malloc returns a pointer. So let's typecast it just to emphasize that point. So double star malloc. We know that table I has the type double star. So it's going to be size of double, because what we want it to point to is not the addresses, we want it to point to doubles now. Okay? So then we know the value is n plus 1, because it says it says of size number of components, which is n plus 1. And that is basically our malloc. So if we have a look at it, we end up with, the first time we run around, we have table 0, malloc size of double, which is 8, times n, let's say n is 2, so 2 plus 1 is 3, so we get 3 doubles. That's probably a lot more than 3. Okay, and we get this memory, and these are all doubles. And so this is the first line of your stuff, which would be your impedance real. Then we do that again, so this will now equal 1. These values don't change, and so we get another 3. Double, 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 and so on. Now, there was a lecture on multidimensional arrays, which when marking we checked who watched. And you should know how to dereference a two-dimensional array. So if I want to access this spot here, I can now do things like table, let's say 0. Let's do the last one actually. 0 n, because n is 2 and my index goes 0, 1, 2. So I'm talking about that spot. And if I go table 0 n equals 4, this will have a 4 in it. Okay. Does that make sense? Does that make sense, Nikhil? Oh, wait. Okay, we'll go through some maths. Cool. All right. So what was the thing? Total parallel impedance. All right, cool. All right, let's go down. What I'm going to do is I'm going to copy and paste that in. Okay. Sorry. What to do? There we go. All right. Just to save me writing this. So invest this in. Okay. So we have our calculate impedance function. Oh, sure. We just got a question. So going back to this one before I go on to the maths, why can't I erase? Sorry. Oh, I'm wrong. Okay. So at the end of your program, as we've said in the labs, you need to free your memory. So to free the memory of, let's say, this X here, we need to free the pointer that points to that memory. So we basically call free X. Now, same with these ones. We can just go free values or free components. However, here, table doesn't point to the allocated memory. Table I, or table 0, table 1, table 2 does. So to free them, we can either do it as a for loop or we can do it as a big thing, blah, blah, blah. And it's just free table I. Yeah. So if you need to free this, you need to go through each one individually because they are the ones that point to the allocated memory. Does that make sense, Ela? I think you did that anyway, so I don't know. All right. So let me just steal more of this. All right. So in the assignments, we had, where's the assignment sheet? We had, if you're doing electronics, engineering, civil engineering, or any of these, and you got this wrong, it's a little worrying because this is a very simple program compared to a lot of the stuff you'll do in the future. So we have Z equals R. So there is no imaginary part. So, yeah, oh my God, why is the pen being silly? Oh, it's because it's copied in the wrong layer. Give me a sec. Okay, so if components, so we're just going through each of the components from I to N. What components I equals, now what was resistor? Was it a 1 or 0? It was a 1. Where are we? So if it's a 1, then we can reference our table, as I showed you before. We can just go results 0, because we're talking about the real part, I equals values I, because the resistance and Z are exactly the same, and results 1 I equals 0. There is no imaginary part. Obviously, 0 times J equals 0. Okay, so the next one was impedance for a capacitor, which is Z equals 0 minus 1 over 2 pi FC J. So here, our values is our C, here, our C, as you got from the user. Our F is our frequency, which is this one. Our pi was a macro. 2 is a number, 1 is a number, negative. And you can see the real part is 0. So else if, I'm just going to write C to save time, equals 2. Results 0i equals 0, because this first part equals 0. And results 1i equals, and now we have to do this calculation, 1 divided by values I, because we're talking about the I component, which probably should be in brackets, times 2 times pi times frequency. And I think there's a bracket there and there's a semicolon. Okay. So the same goes for the inductor. So let me just do this. Laser. Now this one uses macros instead, but you get the point. You should get the point. Sure. So, oops. Get rid of all this. So we've now got all of our impedances for our components. And most people did this fairly well. Got the closing bracer. All right. So now what we want to look at is the complex addition and parallel. Now, basically, if I have a sum of something, let's say I want to add up 1, 2, 3, 4, 5, 6, 7. If I want to add all these up, and I can only do one operation at a time, basically how I add these up is I add these two up, then 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 I add these two up. And that's how I get a sum. Now with summing, when you create your variable, you should start at 0. So there's 7 values there. So 4, I equals 0, I less than 7, I plus plus. To sum all these up, I would just go sum plus equals, and then let's say this is an array. I would just sum up these values. So for our addition, it's pretty much the same thing, except for we're using our function. And we have 2 things to sum. So the first thing I need to do is I'm going to delete this. Sorry. This thing needs to press the wrong thing. Cool. I got rid of most of it. So to sum up the series, basically we need two variables. So let's call it sum real and make it equal 0, and double sum imaginary. Didn't mean that equals 0. Equals 0. Now, as I did before with the simpler example, I used the for loop. If I need to sum something, it's always going to be that I need to look at every value. There's no way. So if I have a bunch of numbers, let's say these are my numbers, there's no way you can sum these, unless you're magic, by skipping one of them. Okay, you need to know all of them to sum them all together. So if we need to sum all of these numbers together, it's just going to be I less than n I plus plus. Now, if we have a look in the assignment sheet, hopefully you have a copy on you. I'm pretty sure it just tells you to do that. So it says create the temporary variables and store the current sum and initialize to 0, which are these two, and then iteratively add to these values. So our complex addition function, let me just copy it. Copy it, paste, kill. So I've got a complex addition function here. Now, it takes in two values for the first number to add, and then two for the second number, and then two out. Now, if we look, no, I deleted it, but when we had the example before, basically what we had done, if we want to add up 1, 2, 3, 4, 5, and we have this sum variable, the first iteration sum is going to equal 1. Okay, then sum is going to equal 3. And the reason for sum equaling 3 is that we are passing the 1 in and the 2 in, and we get the 3 out. With this here, we are passing the 0 in, the 1 in, and we get a 1 out. When we get to the next number, we are passing the 3 in from our last result, which is from here. We're passing the new number 4, and we pass the number 7 out. So the same thing applies here. So we basically, if we have a look at our simple, very, very simple maths, we pass our sum in, and we pass our sum out. Okay, see, this is the old version of the sum, this is the new version. This is old, this is the new, and this is our new number that we're adding in. Okay. So this is old sum, this is old sum, this is new number, this is new number. So it's pretty much the same thing as below, except for we're doing two numbers. Okay. So, as such, we can just go, and I'm just going to write CA instead of complex addition. We can basically just pass our sum real, sum imaginary, our new number, which will be our, I'm just going to write RT for results table. So the real part is stored at 0, and the imaginary is stored at 1. Oops, that should be an I. And then, because we're passing back a pointer, it needs to be an address. So now we have the address of sum R and the address of sum I. Does that make sense so far? Now this is if it's series. Let me know if that makes sense, so then I can continue. Oops. So if that makes sense, then what I'm going to do we just lost someone. All right. Do you want me to go through the parallel one as well?
Not really, Matt, because while doing the assignment, you have already explained it. Thanks a lot.
Okay.
If possible, can you please elaborate more about the bonus one?
The bonus one? Oh, that's easy. So the bonus was kind of easy this time. There's lots of ways you can do it. So the bonus was basically to print out the negative or positive outside. So most of you would have had printf some kind of result table. So ij and the result table I plus 1 j. Yeah? Hello? Okay, so we got that. And most of you would have done something like this plus oh no, we're doing the other version. Sorry. So you would have had something like percent dot 3e plus percent dot 3e, and then we would have j, maybe a line here or whatever. Is that what you had, Yella? Something similar to that?
Yep.
Yep. Okay, so this is when we were printing. No, there's one other thing missing. So to get the signs here, we also put a plus.
Yeah,
Okay.
yeah.
Okay. Now the challenge was to put the sign outside. Okay. So this would print as, I don't know, negative 4 plus negative 3j. But what we wanted was negative 4 minus 3j. So that was the challenge question. So simply, the most simple solution for this is basically if this number is negative, then you print a negative symbol here. And if this number is negative, you print a negative symbol. Else you print a plus here. Else you print a plus here. So we can do this simply by using a ternary statement. Oops. So a plus and a divide, and a minus is just a character. So put %c, and then we can just write our percent dot 3e %c percent dot 3e j, and then a line. Now, for this, all we need to do is check. So we go result table, I, j. Is it negative? If it is, print a minus. If it's not, print a plus. Then we have another problem. So this number now will not print the plus, but it still will print the minus. So we don't want something like this, because obviously that has a different meaning. Okay, they become pluses. So now when we print the number out, we need to print it out as its absolute value. And then you just do the exact same thing for the second one. That's all of it, Hila?
Yeah, thanks.
All right. All right. So I see Jason returned and he asked the question about the parallel. Did you want me to cover that? Or does it make sense from the series? I'm happy to. I might just quickly go over the parallel anyway, but not the code, just the maths. Just because one thing that's different, and which was testing your logic, is the fact that we have Z1 times Z2 divided by Z1 plus Z2. Now, the normal approach to this problem would be that you do all of this in one operation. However, in our case, we can't do that because we can only do an addition or a multiply at one time. So if we calculate this or this, so this this first one, so Z1, is our total. And this one here is our total, and this one here is our new value. Okay. And what we get, so these are the old t. And then when we got out from doing the division is our new t. And we get two of those. The problem here is that with the addition, we got our new t out straight away. However, here, if we do this calculation and store it in our new t, we've overwritten it, and then when we go to do the plus, we're going to use our new t rather than our old t. So this is why you need a temporary variable, because if I have 4 plus 6, then, so let's say we have t equals t, and let's say our new value is 6. If this is our formula, and our total beforehand equals, let's say 4. If we do this calculation, we get 4 plus 6, which equals 10. So now t is equal to 10. So now if we try and do the multiplication, we're doing 10 plus 6. Okay? So now we get 16 here. Oh, it should be times. So we get 60 here, which is incorrect. Okay, we now get 60 over 10, rather than what we want, which would be 6 times 4. So we need a temporary addition variable and a temporary multiplication variable. And then when we do the division, we will get the right number. So then our total will equal Tm over Ta. So instead here, we leave t alone while we do the addition and this, and we get 4 plus 6, which is 10. And we get 4 times 6, which is 24. So now when I do the calculation, it is correct. And it's now 24 over 10. And this is the reason we need these temporary variables. Okay? And I hope you can work that out, because, yeah, that should hopefully make sense. This is why we need the temporary variables, or else you end up with this, where you want this. Does that make sense, Jason? All right. So, any more questions about the assignment or anything else? Or should we leave it there? So I was going to talk about the results of the assignment, but I might leave it for a little bit. I might leave it for this weekend. The results were interesting. Any other questions? Any comments? Anything?
How about the third one, when it will be out?
Sorry, it's written. I just need someone to check it. So
Sorry?
Josh is doing it. So I wrote it, but someone needs to test it first. So Josh is testing it, but he's slow.
And how about the second one's result?
They're done, but we're not releasing them yet.